Maybe here.
No, you don't have to.
I have mine.
Oh, great.
Yep, thank you.
Okay, so we will continue with the AGORA simulations, and to start with a presentation by Santi.
Okay, thank you, Jonathan, and thank you for giving me the opportunity of presenting this the AGORA CosmoRun project. Also, thank you to Joel for the very good review about the AGORA project. I will deep a little bit in some of the things that Joel already talked about in the previous talk. But I will focus mostly on the CosmoRun, the results that are already published, but also many new results that we will be discussing tomorrow in the AGORA workshop. Just to start with, you have, for example, here, this is in fact the CosmoRun galaxy, the 10 to the 12 solar masses halo, the galaxy that is generated in the center. This is at redshift about 0.7 for one of the codes, and I cannot tell you which code is, but this is what you expect for to get at lower redshifts. I will start my talk with this slide that in fact probably most of you already saw before in some of the AGORA talks in the past. It's basically this big summary of what the AGORA collaboration is. And I will not go into the details because also Joel went through them, but I want to make some emphasis on the aim of the AGORA as a collaboration. Basically, the aim was, it was started here in Santa Cruz in this kind of workshops back in 2012 to bring together researchers working in very different code groups that usually work in their own code, including new physics and trying to get better predictions or fit better the observations that are already available, but that barely doesn't talk with each other. And the idea was to take the advantage of having a meeting like this one, that in where many people is talking with one to the other, although they are from different fields, and usually they are more than collaborating, fighting to prove that their code is the best one. So the idea was to get these code groups together and to talk each other and to be able to do steps towards a better understanding of the galaxy formation and evolution, basically knowing which parts of the galaxy formation evolution can be more sensitive to the numerics and which ones are good converged, although you use very different codes. So the idea is that alone, as a code group, you can go very fast because you have your students, your postdocs, you work very hard on making your code to predict better the observations, but it is true that if you can sit with other people with very different views, with very different implementations of for example, the subgrid physics, and try to understand why your results are different, then you get much more insight and you can go much farther on the comprehension of the galaxy formation and evolution. This is the aim and the spirit of the AGORA collaboration in all the papers we already published and for the future ones. Some of the successes of this project, Joel already talked about that, is that we now have a methodology after many years in where we can use the same tools for all the used codes in the community, for example, generating initial conditions, for analyzing the results we are obtaining using any of the codes that are now available in the community, and also a common software for the cooling and heating of the gas. Also, some radiative transfer is included in this Grackle software. Another success, I am just jumping towards the second paper. In the first one, it was dark matter only. Also, we saw good convergence on the dark matter only component. But I want to jump here to this paper because it's an example of what we wanted to do and what we want to do with the CosmoRun. Basically here, 9 different code groups decided to generate semi-initial conditions for a Milky Way-sized galaxy, to run it with a very well-calibrated also stellar feedback. Also, the stellar feedback in this model was well-calibrated, and compare the results. And we observed convergence in some parameters and divergence in some others, okay? But this is, for me, not the most important part of this comparison project in paper 2. The important part is that we developed a methodology to compare the different codes that now can be used in many other research works. Also, we generated the common initial conditions for all of them that are now also publicly available, and also the snapshots at 500 megayears for each one of these models. And basically, after releasing the data, making the public release of the data, many works appeared that are making use or of the initial conditions or of the general, the final models, or also about using the methodology of comparison that we developed for the paper too. After publishing this paper back in 2016, we decided to be a little bit more ambitious and to face this big challenge that is to produce a cosmological simulation using, we invited all the code groups and we wanted to have as large as possible amount of code groups involved to generate this cosmological simulation with, from the same initial conditions, that is the 10 to the 12 Halo mass galaxy. And we did it, we started, we knew the challenge that it is. You know, cosmological simulations depends on lots more parameters than an isolated galaxy model. And of course, we needed to do something that is to calibrate the cosmological simulation to reduce the parameter space that, we have in the cosmological simulations. After 5 years of working, many Zoom meetings, many workshops, we ended up with this calibration strategy. May not be the best calibration strategy, is one of the possible calibrations you can think on, but it's the one we decided to do. And basically the goal of having these calibration steps is to end up with what we call a fiducial set, a default set, a standard set of models for all the codes that are now available to the community that can be used in the future to make further comparisons. So each code group now have a model that is directly compared with all the other models that can be used as a standard for their future comparisons. So they will be able to make intercode and also intracode comparisons if you take this one as a default. Okay, so this is probably the largest achievement we did with this CosmoRun. The idea is that it took us 5 years to do these calibrations, basically because, in fact, it's 4 comparisons in one. We published only one paper, but in fact, these are 4 calibrations, and now I will go through each one of the comparisons. For the first one, very interesting, is a pure collapse. We took the codes and we turned it off cooling heating, we turned it off the star formation, no feedback, and we compared the result of running this simulation, that is the hydrodynamics is already there, dark matter hydrodynamics, but no star formation, no feedback, no cooling and heating. And this is in fact very similar, very equivalent to what was done in the Santa Barbara cluster project, but for a very different initial conditions, okay? And why I am telling you that this is important? Well, because with this test, we are just testing if the integrator is doing or the results of using different integrators, different solvers, if we are implementing properly the resolution and the refinement techniques, if the initial conditions are really read it in the proper way. So we are testing the basics of the simulation. And it is interesting the fact that although this should be done for all the codes when they appear in the community, the Santa Barbara cluster project was done more than 10 years ago and never again. So there are now, all the codes that were used in the Santa Barbara cluster project, not all, but most of them are now not the same ones that are being commonly used in the community. So there are many codes in the community that have never undergone a Santa Barbara cluster project. Okay, so it's interesting to do that just to make a sanity check of also the new codes that are appearing in the community. Okay, in fact, this should be a very easy comparison, very fast, but it took us a while to get the convergence on this calibration step 1. We found many not problems, many differences inside the codes that helped us to solve these differences. Helped us to learn a lot about the insides of each one of the codes, and in fact we also solved some very small coding errors that were present in some of the codes. Okay, so very interesting, the first calibration step. The second calibration step was basically to turn on cooling and heating, no star formation, no stellar feedback yet. And this was basically to test that the Grackle implementation was working well in all the codes. We decided to use Grackle basically because the cooling and heating can be done in very different ways. But we wanted really that all the codes were doing exactly the same. We wanted to be sure that at least for this part of the hydrodynamics, all the codes were doing the same. And this also helped us, for example, to help the community, the Grackle community, to solve some minor differences, minor problems that they had in their code, also in the software. So it was a feedback between the Grackle community and also the Agora community. The third calibration step was to turn on the star formation, but not the feedback yet, okay? And here what we wanted to do is to check if all codes, when you start making stars with slightly different strategies, but for example, keeping the threshold for the density threshold for the star formation, we wanted to see if all codes are generating the same amount of stars, or more or less the same amount of stars, when no feedback is present, okay? For that, we allowed the code groups to use their usual star formation strategy. For example, if they are using deterministic star formation or stochastic star formation, they are using these different approaches. They are not changing their approaches for the star formation, but yes, they are using this threshold. And we finally got quite a good convergence on the stellar mass and redshift of 7. That is a value that doesn't depart much from the 10 to the 9 solar masses for all the codes. And this is also for the calibration step 3. You can see density at the top, stellar particles at the bottom, and in the middle you see the temperature. And clearly here we saw, also in calibration 2 and also in calibration 1, that some minor differences in temperature appear when you use the different codes. This is already published in the paper in 2021. This is something we still do not fully understand. In the paper 2021, we just decided to not go into the details of this because basically when you turn on the feedback, these differences quickly disappear because the feedback hits the gas much more than this heating that is happening because of the collapse of the structures. Okay, so there is something that we still do not understand, and in fact that also appears in the calibration step 1. Okay, and this I will talk about later. That can be another of the future projects in the Agora collaboration. Okay, the final calibration was to turn on the feedback. As Joel said, the feedback, we allow each code group, in fact, we ask each code group to use a feedback strategy as close as possible to the one they are using in their daily science, with the only condition that we wanted all codes to get the same stellar mass as the one predicted by the semi-empirical models, or a similar one, not departing more than 0.2, being between 10 to the 9 and 5 times 10 to the 9, basically, when the prediction is around 2 times 10 to the 9. You have also for the stellar mass versus a stellar halo here, the plots for all the codes at the different redshifts, okay? So this was the only condition, calibration step 4, to get the proper stellar mass and redshift of 4. And from this, we got I told you that we call the fiducial set, the default set, the standard set of the CosmoRun that now can be used by the community to compare intercode, intracode, and their new feedback strategies, their new feedback, their new subgrid strategy, subgrid physics that they are implementing, etc. And the results were, like Joel said, due to we have very different feedback strategies. We have no convergence. This is expected, of course. Nir was telling you, was asking before, that which is the goal, which is the aim of Agora if we cannot reach convergence, because it's clear that we will not reach convergence. We are using very different feedback strategies. The idea of that is basically two things. As I told you, this is a fiducial set, so now each code in the community can use it to compare different implementations of feedback with their own code and with other codes. And second, using so different feedback strategies, if you find convergence in some of the parameters, you will know that this parameter, you cannot use it to constrain your feedback because it's common among codes, although the codes are very different. So it's more about the similarities that are not telling you much than the differences that are expected, okay? This is the different plots. Like Joel already shown you the redshift of 4. I am showing here the evolution for the gas surface density, for the temperature in each one of the codes, for the metallicity at different redshifts, and finally the stellar mass. And something interesting appears here when I show you the stellar mass. That is something I will talk about, and is also interesting for future projects. And after the summary of the CosmoRun, I am now going very fast to the new results. And just to tell you that some of the results, not even the people in the collaboration have seen it, so it will be discussed tomorrow, are the results for the paper we called CosmoRun2. That is a comparison down to redshift 2, and important, we have more than 200 snapshots stored for each one of the codes. The first thing, the halo mass growth from redshift of 8 to redshift of 2. We can see one of the major measures Joel was telling you about, that is at about redshift of 4. Another major measure occurs at around redshift of 2. You can see that the codes agree quite well. It's expected, no, for the dark matter component. This is the stellar mass. Again, I am not showing you which code is which in the colors, just because it's one of the agreements within AGORA. And I am showing you that, 5 minutes. Although this at redshift of 4, the stellar mass was calibrated, we are getting better convergence when we are going to lower redshifts. Something that may be surprising, no? Because nothing is calibrated below redshift of 4. So the convergence in the stellar mass is getting better when we go to lower redshift. And now most of the codes already reached lower redshift. That is something we also discuss and show some results tomorrow in the workshop. I will just skip the movie that was already presented by Joel. Just a comment about this movie is also preliminary. You will see that Chang'e is doing some strange things at about redshift of 7. This is because this model for Chang'e is not the final one. We are getting a new model for Chang'e. Okay. Another of the things that we will be presenting in the CosmoRun2 paper will be the analysis of the resolution at different distances from the galactic center, at different redshifts. And here you can clearly see how the different codes have a slightly different resolution, for example, in the inner part of the galaxy. You can see that this first code looks like the higher resolution. The resolution is not as high in the disk as for other codes, but this is also telling something about doing comparisons at the same redshift for all the codes. And we shouldn't. And why we shouldn't make the comparisons at the same redshift? At least some of the comparisons, because when we analyze the merger tree, these are the merger trees. As we have many snapshots, we can make very detailed merger trees for all the codes. We observe that the mergers, you have redshift 4, redshift 2, that are indicated here by the lines. You can see that the mergers happens slightly different depending on the code. So, for example, if I am showing you at redshift of 2 the resolution elements where they are, you can see that some of the codes are just at redshift 2 having a merger, while some other codes had the merger pretty before than that. So it's normal that if we use the same fixed redshift to make the comparisons, we will end up with some kind of wrong conclusions about, for example, where the resolution elements are. Because if you are having a major merger, of course the resolution elements will not be on a disk, because the disk will not be well designed, no? well settled. So this is something we will do in this paper, to analyze where the major mergers are and to give some values for the moments in where we think we should be comparing some of the parameters that we decided basically to use, for example, a pre-merger stage, because it's when the system is more relaxed. No? We could use post-merger, but if you use post-merger, it depends a lot on how the merger occurred, the time that is needed to relax the system again. No? So if we take just before the major merger, then we are sure that we are more or less relaxed. No? So the idea is to use the pre-merger for the different analysis we will do in the future. Of course, this is preliminary. We will need to discuss that tomorrow in the Agora workshop also. And finishing, again, the idea of this CosmoRun was to make this fiducial set of models. We already did it, And we are now, and I am showing this basically because are plots that were already presented in the paper CosmoRun. Although we are now here, you will see a difference that we are including a new code that already underwent all the calibration steps and is now producing the final CosmoRun model. That is Arepo. You have now not 7 codes, but 8 codes. And also Arepo is converging, calibration 3. You have, this is calibration 2, and also in the temperature density space, you have the 8 codes very well converging in all the calibration steps. So we added a new code, and we are now very happy to help all the possible other versions of codes that wants to join and wants to produce this first model that will be the fiducial one, to produce then many more with different implementations of the feedback recipes for a future comparison. All the data, of course, after publishing the papers, will be made publicly available. This was the agreement in Agora from the very beginning, or through FlatHub, or also we have another possible mirror for that will be, could be Galactica simulations. This is something to be discussed. And finishing the follow-up papers from this CosmoRun paper, one led by Yves Rebats. It's what we call Cosmotechnical paper that is similar to what was the Santa Barbara cluster project, and is to try to understand from where are these differences coming when you have no heating, no cooling, no star formation, but still for the collapse you see that some codes generate some heating around the main galactic halo. This is the strategy that Yves designed to make this comparison, basically to set initial conditions in equilibrium. This will be a gas halo under a fixed potential. Let the halo to be in equilibrium, and then in the calibration 1 you perturb the gas halo, and you see what's happening after perturbing it, and with the cooling off and with the cooling on, and many other possible calibrations will be provided in the future. At least 3 codes are actively participating in this new technical paper. Many more will probably join in the next month after tomorrow's workshop. The circumgalactic medium, I put this picture here only for free, NIRPs, only for you. We're going to analyze the CGM, also Joel talked about that, and is led by Clayton Strawn. The satellite galaxies in the CosmoRun, led by students of Ji-Hoon Kim. And the future projects, that one is led by BKO, that is already in the room also, that is in the room, yeah, I think I saw him. No? Well, it's also to mimic the isolated paper 2, but now including different versions of AGN. So it's, in fact, it's also quite advanced, this project. We also want to make a higher resolution CosmoRun to be able to study clamps. This is something that we will discuss also. A study of the chaos, orbits, bar formation, and spiral arms at lower redshift. And finally, we are also in talks with Jessica Naranian that will participate in tomorrow's meeting to try to make a mock James Webb Space Telescope, or at least to set the tools to do it and to be able to present all the models, the ones that are the fiducial ones, but also the future ones, as James Webb Space Telescope or other mock images for other missions. And okay, for the future, just to undertake these many projects, we need a lot of manpower. It's true that the Agora community is huge. We are many people interested on Agora. The truth is that for the CosmoRun, just because we only needed the code leaders to work on it, to produce the models, we were very few working actively on producing the models, but now that the work will be analysis and will be scientific projects, we need a lot of manpower, and we encourage all the code, all the postdocs and young students especially, but also all the researchers in the field that can be interested to produce new models and to help us with the new projects. Also, sorry, we are thinking something that we missed in Agora is that nobody was really devoted to the Agora project, like with full time. All of us were having other side projects, or all central projects were not Agora. And we think that to speed up the collaboration, we really need to look for research projects devoted to Agora. In fact, many people is already asking for projects to get postdocs, to get PhDs fully inside the Agora collaboration. And we will also try to ask for some CPU time applications in, for example, praise in Europe. Probably this is something we will discuss tomorrow also in the workshop. These are the take-home messages. Again, we invite researchers in galaxy formation observation field to join the effort, to produce their own models with their own favorite feedback. It's not needed. The calibration steps are already produced, so you just need to contact the code leader from your code, and we will be very happy to help you with just get the code with the calibration and run the CosmoRun model with your favorite feedback. It's not needed to go through all the calibration steps. Now, the fiducial model is already there. You just need to run with your favorite feedback to be able to compare with the fiducial set and with also the other models. And let me finish just putting the pictures of the people that we were. We are now maybe almost family after every 15 days meeting in Zoom meetings at very difficult times, at very late at night, some of us, and very early some others. So these are the code leaders. Of course, many other people worked a lot on the CosmoRun. Also, postdocs and PhDs that sincerely, I couldn't find photos in Google half an hour ago. But well, just to say thank you everybody, and also especially to Jihun, that sadly is not going to come in this meeting, but he has been the soul of the Agora collaboration. So I leave it here, and I will take questions.
Hi, thank you for the very comprehensive talk. So you focused on the similarities, but I'm very curious about how the differences actually emerge. And I think it's complicated to answer because of hydrodynamics and different feedback prescriptions and so on. So I'll only ask about the thing that I expected should depend least on hydrodynamics, which is the time of the last major merger. Mm-hmm. And the most extremes that I saw are at redshift 2.4 and close to 1.4, which is a difference of 1.8 gigayears. So can you explain why you think that huge difference is there?
Okay, I was going to go back to we are just studying it. We already saw these differences, these timing differences in the paper one. If you go to the paper one of the collaboration, we already talked about that, about the timing discrepancies. We have many hypotheses, but it is something that we want to study in the CosmoRun paper too. And there are many possibilities from different feedback at the very early stages that makes to appear a delay on the merger history, but also differences on the time step. For example, very small differences in the time step are added and at low redshift can become huge. So there are many hypotheses. We are studying it. Yeah. Yeah, and you're right. It's very difficult to find a specific and focused scientific question when the differences are so huge. So yes, it's also a challenge to try to think on future projects, science projects from the comparison. Yeah, Nir. Sorry, I'm there. Sorry.
Thanks. Very interesting. So when it comes to these comparisons, so we've done comparisons with between Choya and Nix and Enzo and Ramses, and we've published those for cosmological simulations. For PM gravity schemes, you can get extremely good comparisons, something like 0.05% level accuracy in the power spectrum on all scales and redshifts. So I'm not quite sure what is good enough for galaxy formation, but for simple gravity schemes, it's easy, relatively easy to reproduce at sub% level the level of accuracy. What's not easy to do is the hydrodynamics, even for the adiabatic simulations, as you were saying. So one thing that we noticed between these different grid codes, just grid codes that agree well to, with Ramses and Choya agree to within 1% in the matter power spectrum for dark matter. But for gas, there are differences between Enzo and Ramses and Choya and Nix at something like the 10 to 20% level. And we tracked down some of this to the way that the dual energy formalism is treated differently between these different grid codes. And you know, I just thought I'd mention that. So Bruno Villaseñor, who wrote this paper, he came up with a new way of calibrating that, the dual energy formalism implementation, because the temperature, the mean temperature of the intergalactic medium, differs depending on how you do the calibration of that dual energy. So you might look there. That gives you a good way to actually set those parameters in a way that reproduce kind of analytical expectations for how hot the intergalactic medium should be.
Cool, good. Thanks.
Okay, so I think we should move to the next speaker, so Clayton. So we are
Do you need the pointer?
do you have HDMI?